So remember with alkenes, if we add some aqueous acid, we can hydrate them, and so we can add an OH Markovnikov wise. And so can we do the same thing with alkynes? The answer is yes, but it's a pretty slow reaction in most cases. Sometimes it won't be that slow, but in most cases it'll be pretty slow, and that's because the formation of this vinylic carbocation is relatively bad. And so can we still do these hydration reactions with alkynes? The answer is yes, but we need a catalyst to help speed up our reaction. And so the catalyst here, we have our alkyne. We're going to add some acid, some H2SO4 inside of some water, and our acid will be mercury sulfate, right? So similar to the mercury acetate, but somewhat different. And so we're going to go ahead and hydrate these, but what we'll notice is that instead of an alcohol, we end up with our ketone. And so our catalyst here again is our mercury. So let's see how we hydrate this alkyne and how we end up with a ketone instead of an alcohol. So we have our alkyne, we have our mercury 2 plus. The first step is going to be attacking our mercury. And forming our 3-membered ring. Depending on which source you read, you might see a cation or you might see this 3-membered ring. After this, we can have water attack, and it's going to attack the more substituted side as we previously learned. So nothing really new here yet. After this, we're going to get rid of one of these protons through the solvent. So I'm just going to write proton transfer instead of writing out the mechanism, because at this point you should be pretty used to proton transfers. At this step, our alkene will attack another acidic proton. And will be added to the side of the mercury, leaving a positive charge on the other carbon. The mercury then leaves and forms a double bond with the 2 carbons, right? So then the mercury just leaves, and we're left with an alkene. And so this is what's known as an enol. It's essentially a vinylic alcohol. And for the most part, it's relatively unstable. And so since it's unstable, it's going to undergo tautomerization. So what happens here is we have our enol. In this case, it's going to be an acid catalyzed tautomerization. Our alkene will attack this H plus, which will add to the carbon opposite the alcohol. After that, this oxygen will form a double bond in essentially a resonance structure here. And then we simply have a proton transfer, right? This proton right here is going to get taken away by some solvent molecule, and we'll end up with our ketone, which in most cases is going to be the more stable component. And so this is known as keto for ketone, enol for the enol tautomerization. Right, so the enol is relatively unstable, and so it undergoes tautomerization to form a ketone instead. A tautomer is our constitutional isomers. that rapidly interconvert through proton migration. And so what you can tell here is this proton migrated over here onto this carbon, right, to form the more stable structure. The main thing that you kind of want to know here is that these are not resonant structures, right? These have to undergo some kind of chemical change, and they do, right? They do so very rapidly and whatnot, but they are indeed two distinct structures, whereas resonant structures are just drawings of the same compound. And so again, just as a quick review here, you definitely want to know that mechanism. If we have our alkyne, we add some acid, some water, and some of our catalyst, we'll end up with a ketone, right? And count your carbons, 1, 2, 3, 1, 2, 3, right? So you're essentially adding a double bond O here. If you have an asymmetric alkyne, all right, here we have 1, 2, 3, 4, 5 carbons. We can add our ketone to either carbon, right? So we can add it in position number 3 to get this product, or we can add it to position number 4 to get this product, right? So you'll get a mixture of products there. And again, even though you have a terminal alkyne, something like this, you will still end up with a ketone, not an aldehyde, right? And that's because it goes through this enol intermediate, right? Where you can see this OH is now on this inner carbon. And so you always end up with a ketone and not an aldehyde.